So in this video, I'm going to talk about various kinds of transitions we can have between states in atoms and molecules because of the interaction between the atom or the molecule and some external electromagnetic radiation. And so the setup here is that we imagine that there's some particular atom or molecule and it's in some initial state. So let's say we have this state here, which is an energy eigenstate with some particular energy. And so we can imagine that an atom is initially in that state. And now we want to think about this electromagnetic wave. And so this might be coming along, just some radiation, light, or radio waves, or something else, and it comes along and it now interacts with the atom or the molecule. And so physically, that electromagnetic wave has an oscillating electric field and an oscillating magnetic field, and the electric field is going to exert a force on any charged particles in the atom or the molecule. And similarly, the magnetic field will exert forces if those charged particles are moving. And so we have this physical interaction, and eventually the electromagnetic wave passes by. And then the result of that is that our atom or molecule, it might end up in a different state. And it could be, in general, some superposition of various states. Some of them might have a higher energy than the original state. Some of them might have a lower energy. But we'll think about calculating the probabilities for transitions to particular states. And later, we're going to use time-dependent perturbation theory to do those calculations. But in this video, let's just talk about the different possibilities and introduce some terminology for what are the kinds of processes that can happen. Okay, and so the first thing that we can have would be the possible transitions. Okay, so the first thing we can have is, number one, a transition to a higher energy state and that would be interpreted as you are absorbing some energy from the electromagnetic wave. So you have some energy in the electromagnetic wave, and then as a result of this interaction, the atom or the molecule absorbs some of that energy and goes to this higher energy state. At the quantum level, really what's happening is that atom or that molecule, we say it's absorbing a photon. Okay, so it's absorbing some particle of the electromagnetic radiation. And we saw in the last video that these transitions are much more probable if the frequency of the perturbation matches with the energy level difference in your atom divided by h bar. Okay, and so now this has a very physical interpretation. So in radiation with a particular frequency, the photons all have a certain energy. And when that photon energy is matching with the difference in energies between your state A and some higher energy state B, so let's write that there. Okay, so if your frequency matches EB minus EA over h bar, that means that the photons in that radiation will have the same energy as that energy difference between the two states. And so we can then understand, why is it then so much more likely to make that transition? It's because then by absorbing a single photon, then the atom or the molecule has enough energy to go from your original state to the higher state. So these transitions are understood quantum mechanically in terms of photon absorption. And we can schematically represent that as the photon coming in, and then the atom goes from a lower state to a higher energy state. And this process is called, normally we just use the word absorption. Okay, so we're just going to call that kind of a transition absorption of a photon. The next one we would have kind of the opposite. So this is a little bit counterintuitive. What we saw in the last video is that if you have a frequency that matches an energy difference between your state and some lower energy state, then you still have a high probability or a higher probability of making a transition. And so what we can have is a transition to a lower energy state. Okay, and that kind of looks like this, where again, you have a photon of your electromagnetic radiation. The energy of that photon matches the energy difference between your initial state A and some other state B. And then what happens is that you can have a transition down to this lower energy state. So that is a bit counterintuitive because it seems like you're adding energy from this photon coming in. But what happens is that, so obviously because the atom has a transition down to a low energy state, you're going to be giving up some energy. And so what happens is, from this photon point of view, you have a photon coming in, and then we say that photon stimulates the emission of another photon. So you have one photon coming in, it interacts with your atom in this higher energy state A, and then because the energy of the photon matches this frequency difference, or matches the energy difference between your two states, it turns out that that will give you then a higher probability of making a transition down. And if you do make that transition down, what happens is that now you have an extra photon. The energy from the atom goes into making another photon. And so you have one photon going in, two photons coming out. Okay, and so this is the process that we call stimulated emission. Okay, and there's actually a third kind of atomic transition that we will talk about a couple of videos from now. And this one actually doesn't involve any incoming radiation at all. This can happen even if you have an atom which is all by itself in some energy eigenstate, which is not the ground state. So what we'll see is that you could actually have, say, an atom in this state A, and then actually just by something like we would say a spontaneous process, the atom can make a transition down to a lower energy state, and where does the energy go? It is emitted in a photon. So we can have, that looks like this, where you have your state A, some lower energy state B, and then the atom or the molecule makes a transition down to this lower energy state, and you emit a photon. And so that one is called spontaneous emission. And that one seems a little bizarre at first because the state A was supposed to be some energy eigenstate of this molecule, and we learned that energy eigenstates are time independent. They're supposed to be stationary states. If you have an energy eigenstate, nothing is supposed to happen with it. So how are we saying that the state is in the state A and then it makes a transition spontaneously to a lower energy state B? And so the resolution of that puzzle is that when we originally were thinking about atoms or molecules and calculating these energy eigenstates, we just wrote down a Hamiltonian for the various charged particles in the atom. But in reality, those charged particles are part of a larger system that includes the electric and magnetic fields. And quantum mechanically, even though you might not have any classical electromagnetic radiation around, if you have an atom that has some energy that's higher than its ground state energy, then you have a possibility to transfer that energy from the atom to the surrounding electric and magnetic fields. It's just if you put energy into one part of a physical system that's connected to other parts, then that energy can actually move around and it can be transferred. And so if you think about the full system of the atom or the molecule coupled to the electromagnetic fields, then in that full system, these excited states of your atom or your molecule, it turns out those are not true energy eigenstates of the full system. And so they can, in fact, make some transition down to the ground state where you have emitted a photon. Okay, so in the next video, we're going to actually talk about how do we use time-dependent perturbation theory to calculate the probabilities for all of these things to happen, the probability for absorption, the probability for stimulated emission, and the probability for spontaneous emission.